Here's another example. You can imagine that for different kinds of transport systems, whether it's a bike, a car, a truck, a plane, the heavier the material of construction, the greater is the fuel consumption. So over the lifetime of using that transportation system, you have an initial cost because of it having been fabricated by a certain material and meeting a certain design, and then the overall fuel consumption. And the greater the mass, the greater the fuel cost. So the penalty function z, which is a function of the cost and the mass, along with this exchange constant of dollar per kilogram, allows us to estimate what is the lowest z. So what is the value of alpha? It turns out in practice that for steel, the alpha is in the range of 3 to 6 depending upon the alloy conditions. Also, for certain higher alloy steels or for aluminum, the exchange constant can be higher. Or for certain kinds of glass reinforced composites, you could have like a higher, you would pay that much more for a more expensive material to reduce a kilogram of weight, because the densities keep reducing over here as you go from steels to composites. And then you're willing to, for space expeditions, for instance, or defense applications, or for aerospace sectors, you're able to work with a much more expensive material just to be able to save on fuel over the lifetime of the material. It turns out that the bubble charts that we can create using EduPack are very useful for being able to determine alpha and z, okay, for this type of optimization. So for instance, in the case of metric P2 versus metric P1, right, in this first case it's mass on the y-axis and c on the x-axis. You have range from light to heavy on the y-axis, cheap to expensive on the x-axis. You can begin to minimize z for a given value of alpha by working through a bunch of parallel lines. If you change alpha, then you would be able to change the slope and then work out another z, and you get a best choice. If instead you go to log scales, as we mostly represent a lot of our performance metrics, you end up having these kinds of contours created instead of these nice lines. And we select decreasing values of z based on these types of intersection with the trade-off surface. One of the nice things about EduPack is you can basically plot complicated values for x and y terms. You can, for instance, plot density versus Young's modulus, or density, right? Or price times density divided by Young's modulus. We took a look at that in terms of how to compute those during the previous week. So this is what the log plot would look like on a bubble chart created by EduPack. So there would be a way to be able to represent a trade-off curve visually based on something that would lie over here, and then we look for different slopes. If you now, after you created this bubble chart, if you click on the axis, x and y axis, and you convert them to linear scales, this is how this overall selection will get modified as represented over here. If we take now this particular plot, we can now use a line tool and apply a slope. The slope would be minus 1 over alpha, and arbitrarily if we choose alpha to be 1, in this case it will be minus 1 as a slope. We could choose for different values of alpha slopes on the EduPack chart mode, and accordingly you can decide what is the optimal solution, and then you select the minimum index. If you now, after you've drawn this line, if you go ahead, change it back to the log curve, you will be able to generate this type of a z. Look at the difference, the log curve over here, and you'll begin to select the specific points which are harder to see over here, but easier to visualize going to this particular scenario, right? Something around here is what we're looking at as options. Then we use our judgment to see which of those make better sense as far as a material that would be suitable for the design. We can go through this in an iterative manner where we choose different values of alpha and come down to creating a set of contours based on different values of z. Alternatively, we can also look at plotting mass relative to a particular material, say steel. So we could on EduPack plot M over M naught, and that corresponds to a cost of C over C naught. And now you're looking at a modified alpha star where we know that this is your existing material and you're looking for something that is either cheaper or is lighter while still meeting the design constraint as opposed to going somewhere else. So to summarize, we have looked at for a function something where you have many constraints and one objective, and we have looked at identifying the property, screening constraints, and ranking the property or index. Alternatively, you have a situation where you have many constraints and two objectives, and in that case, you construct these trade-off plots. The more complicated scenario where you have many constraints and more than two objectives involves progressing from a penalty function that we've outlined to getting to an exchange constant. We will leave that out of our consideration for now, but continue during the next week to look at how to be able to deal with situations where you have many constraints and two objectives. So we will build off from this in the next class, which is lecture 10, using the second design exercise where we begin to look at first different ways to compute material indices, and then look at where the optimization can be done with one or more objectives. So this is the basis of chapter 7. There is a quiz 3 that is due by the end of Sunday, so make sure that you submit that. We will conclude this lecture with a segment of a few case studies involving derivation of material indices and their use in material selection, compiled by some students from mechanical engineering at the University of Louisville. See you then.